Okay. Unshare. Oh no, is that raise hand? Whoops. Yes.
Test. Okay, welcome everybody. This is the IRTF Open meeting at IETF116 in Yokohama. My name is Colin Perkins. I'm the IRTF chair. Can I just check that everything's working for the remote people? I'm very quiet. Is that better? All right. Okay, so as I said, my name is Colin Perkins. I'm the IRTF chair. This is the IRTF Open meeting. So I want to start with the usual reminders of the IETF policies, the intellectual property policy, and so on. So first of all, a reminder that in the IETF we follow the same IPR disclosure rules as the IETF does, and that by participating in this meeting, you agree to follow those procedures. In particular, if you're aware of any intellectual property on your talk or your contribution at the microphone, then you need to disclose that fact. And the precise rules for this are listed on the slide and so on. In addition, a reminder that we make audio-video recordings of these sessions available. This session in particular is being streamed live and going out on YouTube, and the recording will be on YouTube afterwards. And there's also a photographer here, so if you're wearing one of the red "Do Not Photograph" lanyards, then you will avoid the photographs, but if you speak at the microphones or if you are giving a presentation, you will be recorded and the recordings will go online. We also have a code of conduct. Please do pay attention to the rules about code of conduct and the anti-harassment procedures. Please do behave professionally and appropriately, and ensure that everybody is welcome in this meeting and in the IRTF and in the IETF in general. A reminder also that any personal data you give will be handled in accordance with the privacy policy. If you are a remote participant, please remember to turn off your audio and video unless you're actively asking questions. If you're a local participant, please do sign in by scanning the QR code so we have a record of who is attending. Also, if you are asking questions, please use the MeetEcho tool, either the on-site tool if you're in the room or the full tool if you're remote. We're running a unified queue for questions, so please do use the tool rather than just going straight up to the microphone to put yourself into the queue. And if you have any questions with this and how the tools work, the URL on the slide has some further information. Also, a reminder that as a COVID safety measure, in-person participants in this meeting and in the other IETF controlled rooms are required to wear an FFP2 mask or equivalent. The only exceptions to that are the people actively presenting and the chair when they're actively speaking. Participants asking questions from the floor are expected to remain masked. All right, so as I said, this is the IRTF Open meeting. The IRTF itself is a parallel organization to the IETF, which focuses on some of the longer-term research issues which affect the internet. It's very much a research organization. We're not here to conduct standards development. We're not here to produce standards. And while the IRTF can publish informational or experimental RFCs, the primary output of the research groups is expected to be understanding and research papers rather than protocol specifications and RFCs. The IRTF is organized as a number of research groups. Those listed in and shown in dark blue on the slide are meeting later this week. The Computation in the Network Research Group, CoinRG, met this morning. And we have two groups which are not meeting. The Network Coding Research Group is essentially finished with its work and will be expected to close relatively shortly. And the Thing-to-Thing research group is having a meeting in a few weeks online. And all the other groups are meeting later this week. We also have two new research groups, two new proposed research groups, which are meeting for the first time later this week. We'll hear more about these in a few minutes. First of these is the Usable Formal Methods Research Group, which is chaired by Jonathan Hoyland and Stephen Farrell. The goal here is to bring together the protocol standards community in the IETF with the academic research community, which is studying formal methods for protocol specification. The idea being to exchange some experience and ideas and to try and understand whether and how formal methods can be employed to improve the way we specify protocols and to improve the correctness of the protocols that are being specified in the IETF. And to pass back experience on what's useful for professional protocol designers to the academic community developing such tooling. And that group will be meeting on Wednesday, I believe. The other new research group is the Research and Analysis of Standards Setting Processes proposed research group, which will be meeting on Thursday. The chairs for this are Ignacio Castro and Niels Ternova. And this group is focused on understanding the standard setting process itself. It's focused on understanding the community, its diversity, the impact that the set of participants in that community have on the process by which we develop standards, the impact of how changes in that community affect the standards which are being developed. It's focusing on understanding the decision-making process in internet standards, and understanding the interactions between the different parts of the IETF, the participants in the IETF, and the IETF and other standard setting communities. As I say, we'll hear more about these in a few minutes, and please do consider going along to their first meetings later this week. So as I said, the primary focus of the IRTF is on producing understanding and research, and most of the outputs are in the form of papers. We do, however, publish RFCs occasionally, and the IRTF has published 2 RFCs since the last meeting. The first of those was the CCN info draft, which came out of the Information-Centric Networking Research Group, which is an RFC published in February this year. And I think just last week, the Quantum Internet Research Group published its first draft, the first RFC on the architectural principles for a quantum internet. And the Quantum Internet Group is meeting in the slot immediately following this one. So if you're interested in that topic, please do go along to that meeting. In addition to the research groups and the research we do in those research groups, we also organize the Applied Networking Research Prize. This is organized in cooperation with the Internet Society, with sponsorship from Comcast and NBC Universal. And it's here to recognize some of the best research results in applied networking, some new research that has potential relevance to the Internet standards community, and perhaps to recognize upcoming people who are likely to have an impact on the Internet standards and technologies going forward. I'm very pleased to announce that we have 2 ANRP award presentations today. The awards go to the awards for this meeting go to Boris Pizmeny for his work on novel offloading architectures for NICs, and to Arthur Seller-Jacobs for his work on evaluating machine learning for network security. So as I say, the main focus of this meeting will be on these presentations. The papers and the awards, the papers and the slides are all online on the website. And please do congratulate the 2 awardees for the awards. In addition, the final activity we organize in the IRTF is the Applied Networking Research Workshop. The workshop is a forum for the research community, the vendors, the operators in the IETF standards community to present and discuss emerging results in applied networking research. It co-locates with the July IETF meeting, which will be in San Francisco this year. And I'm pleased to announce that the chairs of this meeting, of this workshop, will be Francis Yan from Microsoft and Maria Apostolaki from Princeton, both of whom are previous ANRP winners. So I'm very pleased to have them on board and running this workshop. Paper submissions for the workshop will be due on the 12th of May, and you should look out for the detailed call for papers any day now. Finally, I'd like to highlight that we do offer travel grants to attend the IRTF meetings. We offer diversity travel grants to support early career academics and PhD students from underrepresented groups. And we also offer travel grants to attend the Applied Networking Research Workshop. The IETF.org/travel grants site will include information about those. You can expect the call for travel grants for the July meeting to go live later this month. So please do look out for that in the next couple of weeks. And that's essentially all I have to say. Our agenda for the rest of today. We are starting with a couple of short talks introducing the two new proposed research groups. Jonathan will talk about the usable formal methods group next, and that will be followed by Ignacio, who will be talking about the research and analysis of standard setting processes group. And then following that, the majority of the meeting will be devoted to the award talks, starting with Boris talking about autonomous NIC offloads, and then Arthur will be talking about AI and machine learning for network security. If there are any questions, if not, Jonathan, I guess you're first.
Do you want me to request share slides?
No, I'm just doing it. You should have control.
Yeah. Okay, good afternoon. Good afternoon, everybody. So I'd like to introduce the Usable Formal Methods Research Group. And before I do that, you probably want to know what I mean by formal methods. And the standard definition would be the use of mathematical techniques and formalisms to assist in the specification, design, analysis, and implementation of, in this case, protocols. But that's not really a very easily digestible definition. And so the real question is, can we bring mathematical rigor to our work with protocols? Can we say, this protocol is secure and I can prove it? So a very, very abridged history of formal methods. I am going to try and compress approximately 70 years of history into one slide. Yes, there are lots of things missing, but basically work in the 50s and 60s that mostly dealt with safety and whether mechanical processes would fail. And over time, that was applied more and more to digital processes. And nowadays, we use it to analyze protocols. And certainly initially, the proof techniques were really quite limited. We had to make these very strange assumptions, or we couldn't even analyze some things. They were beyond our tools. And they required huge amounts of manual work, hundreds and hundreds of pages of by handwritten algebra. And so over time, we eventually invented tools and techniques that helped with this process and allowed us to do more interesting things. And eventually, the tools were sufficiently mature and usable that the formal methods community became deeply involved in the development and specification of what became TLS 1.3. And just to give you the way I think about this, you can very roughly decompose formal methods into two rough camps. There are lots of things that don't really fit into this categorization, but roughly, you would say formal analysis is the set of techniques which we use to say, is this specification design correct? So ignoring anything that we care about the implementation, is the design, if implemented perfectly, correct? Does it do what we think it does? And then there's the second half, which is formal verification, which says, does this piece of code do what we think it does? Does this piece of code say, compute the right value? And the formal methods research group will try and look at both of these. Just to go back briefly to the TLS design process, what happened with TLS 1.3 was from the beginning, academics were doing formal analyses of the protocol design. They were saying, does this design achieve the effects we want it to? And actually, there were 3 or 4 major flaws that were found in the protocol design at various stages of its development that eventually were removed. Well, they were removed, and there were proofs written that say this version of the protocol is secure. This version of the protocol meets its meets its specification requirements. And that is where I first became involved in the IETF. And so you might think, oh, okay, well, we've already used this tool. We know how to do it. Great, problem solved. Problem is, there we go. The problem is formal methods are not very user-friendly. The proofs can be immensely long. So we used an automated tool to do a proof of TLS 1.3, and the proof runs to 750,000 lines. And you could, in theory, go through line by line and check each one of those, but most people don't want to. And so you basically have to choose a tool that checks each line and eventually gets to the end. The alternative procedure that people use, rather than trying to use one of these tools, is to write by hand proofs, literally long form proofs. And quite often I will be asked, can you review this paper? Here is 26 pages of algebra. You have 2 days to review this paper. And unsurprisingly, it's very, very difficult to actually check whether the proof is actually a proof. And so there are a couple of issues, but mostly the proofs are hard to understand, to verify, adjust everything. And academics have mostly been doing this work. And the problem with this work is it's very high risk and very low reward, because quite often what happens is you analyze a protocol and you say, ah, great, it's secure, no problems at all. And then you go to get it published and everyone's like, who thought it wasn't secure? You just have written a very boring paper. And so unless you're like, I'm pretty sure this is broken, you're not going to invest the potentially years it would take to check. And so enter the usable formal methods research group proposed. How can we solve these problems? How can we take this technique that we've finally gotten to a point where we can actually use it? How do we make it so that anyone can use it? And I think the initial steps that will be really good for the UFMRG is it's going to provide a place for experts to gather. And it will be a pool of knowledge that other working groups can come to and say, we can't make this work. We don't know how to do this. Can you advise? And if we then start building up a tower, training materials, because at the moment, it's very easy to analyze a very tiny protocol. There's examples, and then the moment you want to go slightly more complicated, you're on your own. And we can also provide feedback to tool designers. So a lot of the tools are not actually used necessarily by people who want to analyze IETF protocols. They're used in academia. So we can go to them and say, we need this feature. Hopefully, because the IRTF does do some publishing, we'll have a place to publish these negative results, place to publish, here is a proof of security, and we'll have a place to store all the proofs and the checking tools you need to check the proofs. So a couple of non-goals. Very important non-goal is to not try and change the IETF process. So maybe the IETF processes do need to change, but that's not what we're interested in. That's not our job. It's an IRTF group. And if we manage, the way we can check whether we have succeeded in making formal methods usable is if people use them. If we say, you have to use them, we don't know whether we've succeeded. And very much, we don't want to be an obstacle. We want to provide useful tools. We're meeting on Wednesday at 9:30. Please come and join us. Thank you. Any questions?
All right, thank you. Does anyone have any questions? Rod.
Ooh, I guess I won the online lottery there. I've got the really low mic. All right. So maybe this is a question for when you have the session later in the week, but my very, very limited understanding of formal methods is that one of the challenges with them is anytime you're doing a proof, you're always dependent on a certain set of lemmas or a certain set of assumptions.
Yeah.
So the big question is whether or not those are valid. Does
sure.
that fit within the scope of what you're planning on working on?
So absolutely. There are some very standard assumptions that we make, which we know aren't true. For example, we assume that, say, asymmetric crypto is just a magic perfect black box and that it always works. And yes, we will definitely need people who do cryptanalysis to continue doing their work. But the goal of these proofs is to say, if we assume that we have a valid or a secure asymmetric cryptography algorithm, we can then swap that out with any other algorithm that we think is secure of the day, and it doesn't change the proof. The proof says, if you have a secure algorithm, you can build this thing.
Thanks. And sorry, Colin introduced me, but I forgot to say my name at the beginning. For the record, Rod Van Meter.
Hello, Diego Lopez, Telefónica. Just a question, because looking at, when coming here, I was assuming that, well, the formal methods were going to, 1 second. I will. No, it's better, yes. No, I was understanding that we're talking about formal methods in general for protocols and for verifying or proving whatever the properties, but it seems that you are focusing it very much on security properties. Yes.
So that security properties is my background, but it's certainly not the only scope of the RG, the proposed RG. You know, one of the first things we're planning to do is try and come up with some examples that people can look at that aren't security related, you know, deadlock related, live lock related. But yes, that's certainly in our scope. But yes, my background is security, so that's what I think about.
And just, do you have any idea of the background that you're planning? Because I remember a long time ago, this I used to work with this communicating process algebra and things like that.
CSP.
Yeah, exactly. It's or are we talking about something a little bit ahead of that?
Definitely something a little bit ahead of CSP. CSP is 92, 93.
Yeah, well, even before, I would say, yes.
So yeah, we're looking at things from several decades later than that. Yes.
But somehow based on related approaches, or just
so the underlying tool is usually either pattern matching recursion schemes or higher order recursion schemes.
Okay.
Any other questions?
More questions? All right. Thank
Okay.
you.
Thank you very much, and come to my RG.
Come to the RG, yes.
Come to my bot.
Right, right. All right, next up is Ignacio, who'll be talking about the RASP RG. A reminder, while Ignacio is getting set up, if you're in this room, you need to wear a mask. And if you are not willing to wear a mask, you need to leave this room. All right, Ignacio, over to you.
Thanks, Colin. Hello, everybody. Telling you about our new research group, proposed research group, RASP, which is about research analysis of standard setting processes. And I'm chairing it together with Niels. Next slide, please. So what is RASP about? Well, the name says it all. It's about understanding better the things that we do here, not only at the IETF, but mostly at the IETF. The point is not to judge whether the IETF is the best thing since sliced bread and the ITU is not. The point is just to analyze what we do, and other people might make judgments on that, but that's not really the point of this research group. The point is data rather than judgment. Types of outputs that we expect, joint reports, research papers, databases. For example, we are now labeling email discussions for agreement, disagreement, so we can understand better consensus formation processes. Tools and open software. We're, for example, making a little tool to make recommendations for cross-area review by comparing the content of the emails of the people with a draft that might require review. The way to do it, well, similar to many other research groups, collaborations. There's many different people from many different areas that are interested in this sort of stuff. Organizing working sessions and prevent duplication. There are different people that has been working in different ways around this, and mostly produce evidence-based reproducible work. This is the charter. Please subscribe to the mail list if this sounds interesting. Come to the session tomorrow. We do a lot of different things. Next slide, please. Just to give a glance, like this, for example, is from one of the papers that we have been working on, and this is the co-authorship graph. You can see how it's a group of people that write a lot of drafts together. You can see also some points in the middle. You can guess maybe why that's happening. Again, data, not judgment. Next slide. That's the interaction graph of the working groups, and you can see how things cluster nicely around different areas. And this is just to give you a glimpse, but we do many other things. And if you have, next slide, please. If you have questions or you have ideas or you want us to look into something, please drop by. And this is what we do. What we don't is to make hierarchical comparisons between which standard setting organization is better, or similar to what Jonathan said, define how operational process of the IETF should work. Though people is welcome to use the data that we might produce to make those judgments by themselves, but that's not our role. Next slide. So please drop by on Thursday. We have, I believe, a very cool session going from ethnography to large language models in understanding the IETF. And please come to agree, disagree, propose, or just discuss. The research group is starting, so if you want to have a say on things that we should be looking at, we are all ears. Thank you very much.
All right. All right.
If there are any questions.
Thank you, Ignacio. Any questions? Guess not. Don't see any online. Let's call for questions. Okay, well, if you are interested in understanding how the IETF works, please go along to the meeting on Thursday. Thank you. All right, and again, a reminder that we have a masking policy, and that if you're in this room, you need to wear a face mask. And if you are sitting next to someone who is not wearing a face mask, please remind them. And if you're not willing to do that, you need to leave the room.
Hi, everyone. My name is Boris Pismeni.
Hang on. Just 1 second. All right, so with any luck, you now have control of the slides. Okay, so I'm very pleased to introduce the first of our Applied Networking Research Prize winners. First of our Applied Networking Research Prize winners for this meeting. The first speaker here is Boris Pismeni. Boris is a PhD student at the Technion Computer Science Department in Israel and is currently visiting EPFL. He's also employed by NVIDIA as a software architect. His research is focused on improving system software performance by enhancing NIC controller hardware. And in recent years, he's worked on accelerating QUIC with UDP segmentation offload and receive-side coalescing offload. He's also worked on accelerating encryption for QUIC, TLS, and IPsec. His talk today is on autonomous NIC offloads, and it's a paper that was originally presented at the ASPLOS conference in 2021, if I remember correctly. Yes. All right, so congratulations again to Boris, and over to you.
Thank you. Okay, so thanks for the introduction, Colin. This paper is autonomous NIC offloads. It describes a software hardware architecture that enables NICs to accelerate layer 5 protocol computations transparently to software TCP/IP. So we're going to focus on layer 5 protocols over TCP. Here are some examples. Specifically, we're going to focus on the TLS protocol and its encryption, decryption, and authentication, or digest as it's called here. In the paper, we also present NVMe TCP and its digest and copy offload and the combination of the two. So a brief overview of TLS, although you probably know better than I about this protocol. Most popular way to encrypt TCP traffic has two stages, a handshake and a data transfer. The data intensive portion is the data transfer, so we focus on that, and we can assume that the handshake has been completed for the rest of the talk. Okay, so next we're going to explore the design space of layer 5 protocol acceleration using TLS as an example, TLS encryption. So the first approach to accelerate TLS is in software. For instance, kernel TLS is a software optimization that requires no additional hardware, and we'll see later a bit in more detail how it optimizes TLS, but essentially it breaks some abstractions to make it more performant. The problem is that as long as we're using software, we can't avoid the overhead of data-intensive computations. So the next approach is to use hardware, such as the on-CPU acceleration available in Intel CPU cores called ASNI. So this is very efficient. It uses fast CPU registers and cache memory, has relatively low overhead. But nevertheless, a CPU core doing TLS can consume more than 50% of the core on just encryption. So looking further, we can consider an off-CPU accelerator, such as a PCIe card that does encryption, like the Intel Quick Assist card. The benefit is that the CPU overhead is independent of the data size being encrypted, but the problem is that significant parallelism is required to outperform the on-CPU acceleration. And this can be problematic, and sometimes applications need to be redesigned to make use of that. Looking forward, we can ideally place the encryption on the NIC itself, as data needs to traverse the NIC anyway. The problem is that current approaches to do this, they depend on offloading TCP, IP routing, quality of service, essentially the entire network stack into the hardware, and this introduces a lot of complexity, security problems, and has thus far shown itself to be undesirable and impractical. So our approach is to move the encryption to the NIC while still keeping the network stack in software, including TCP/IP, etc. The problem with our approach is that we introduce additional overhead on recovery from reordering and loss, as I'll explain next. So before we dive into how autonomous offload works, we build our solution on top of kernel TLS. So I'm going to explain how kernel TLS works. So kernel TLS is a form of software specialization. So before kernel TLS, what we had is we have a baseline application, say using a TLS library. It calls the library with its data. The library encrypts the data. It puts it in a TLS record. And then the record moves to the kernel where TCP sends it. So we have an encryption pass and a copy pass. Once when passing from the application to TLS, and the copy is when passing from TLS to. I lost control.
You lost control.
Okay, and the copy is when passing from TLS to TCP/IP. So what kernel TLS does is it combines the encryption and the copy pass into a single pass, and so it could be more efficient. Additionally, it enables optimizations such as send file. Finally, in kernel TLS, the TLS layer can communicate directly with the NIC driver, and this is what we require for autonomous offload. This direct communication allows us to make some optimizations. So with autonomous TLS, what we have is that we eliminate the encryption pass from software and we move it into the hardware. So when the application sends it data using kernel TLS, we just do a copy, we don't do the encryption, but we still create a record. But this time we can't compute some parts of the record. For instance, the MAC, the authentication, it remains 0 because we can't compute it. And we pass this data to TCP unmodified, and TCP will add its headers and segment it as it desires. And eventually, when data passes from memory to the network, the NIC will encrypt the data as it passes through. So in a nutshell, this is the solution. Now we'll get into how we implement the offload, starting from the transmit side. In order to offload data that is in sequence, we don't need to do much because the NIC uses a state that incrementally is updated, and we simply send the packet with an indication, and hardware will perform its operation and encrypt the data. The NIC uses two contexts to accomplish this operation: a static state, which is relatively constant for the entire connection. It holds, for example, the encryption keys, and a dynamic state that is updated for each and every packet, and it holds the state for the next expected TCP sequence number. So it tells the hardware how to encrypt the next TCP sequence number position. And it holds things like the current message offset, the current message size, and the IV, and the rolling authentication or ICV state. Lost control again. Okay.
Share it with you.
Okay. So the problem is when we want to send something that is out of sequence. For example, assume that we send packets 1 through 8, and then software decides to retransmit packet 5. So the hardware doesn't have the correct dynamic state to accomplish that because it expects packet 9 and it needs to transmit packet 5. So what happens is that the driver identifies this problem. It compares the sequence numbers between the dynamic state it has a shadow of and the packet that's being transmitted. And it's going to perform a flow which we call recovery to transmit packet 5. So in the recovery flow, what we need to do is we need to pass the TLS record prefix of TCP packet 5, which is marked in the dashed lines on the figure. And after passing this information to NIC hardware, we can send packet 5 because the dynamic state would be adjusted for packet 5. And to accomplish this, the driver will communicate with the TLS layer directly, asking it for this TLS record prefix. And the TLS layer, it holds this mapping, which allows it to provide this information. The only problem is that the TLS layer needs to hold this information all the time, and we can't release this data once packets are acknowledged, because we may release a part of a record, so we hold an extra reference for all the packets that that combine into a record, and we release those only when the entire TLS record is acknowledged. So that's it for the transmit path. Moving to the receive path. So again, on receive, the in-sequence flow is very straightforward. Hardware decrypts incrementally as packets go through and indicates for each packet whether it was decrypted and authenticated successfully. Now, problems begin when we have out-of-order retransmissions. For instance, in this example, we receive packets 1, 2, 3, 4, and then packet 2 again. So packet 2 is a retransmission, and then packet 5. So what will happen is that hardware will skip the decryption of packet 2, identifying that it was received before because it expects packet 5. The benefit here is that hardware continues doing its acceleration for packet 5 and onwards, and it doesn't stop because of packet 2. Another problem that may occur is TLS record data reordering. So here what we have is that packet 2 is not received where it is expected, and instead packets 3, 4, and 5 arrive, and only then packet 2 arrives. So packet 2 was essentially reordered and received later. What happens in this situation is that using the length field of the TLS record header, we identify that the next record header will appear in packet 3. And so when packet 3 is received, the hardware resynchronizes itself to be ready to decrypt the record that starts in packet 3. And so packets 4 and 5 will get decrypted, and the offload and the acceleration will continue for future packets. And then packet 2 is considered to be a retransmission in this case. Now, the real problem happens when on the receive path, we get header reordering. So when the TLS record header is reordered, the hardware can't use this trick where it relies on the length field of the TLS record header to tell the position of the next record, because after it receives packet 4, it knows it didn't see packet 3, and packet 4 can have any number of potential TLS records. And as a result, it stops offloading until it is recovered, until the hardware state is recovered.
It's just a little slow, I think.
Okay. So to solve this problem, we can't just let software notify hardware every time here's a TLS record header, and here's a TLS record header, because packets may continue coming all the time. And as a result, we will always have this race condition between software and hardware, where software is chasing hardware and hardware keeps receiving new packets. So we need some solution that is not pure software to solve this problem for streaming TCP workloads. And the solution we propose, we devise, is a software-hardware collaboration, where first, so suppose we have TLS header reordering, and what hardware does, it will speculatively search for what we call a header magic pattern. For instance, for TLS, it's this hex 170303, which represents the type and the version. And once hardware identifies this pattern in the TCP byte stream, it will ask software, is this a TLS header or is it something else? And meanwhile, packets continue to arrive, and the hardware will track where it expects to see subsequent TLS record headers based on the length field again. So here we first found the header in packet 5, and then in packet 7, we check and verify again that the header is still there. If it's not there, we go back to step 1 because it was wrong. But if hardware was correct in this speculation, eventually software will be able to confirm that indeed packet 5 contained a TLS record header in the position that the NIC asked about. And this will allow hardware to synchronize and resume its acceleration from whichever point it is currently tracking. So this is essentially how we solve the recovery problem on the receive side. Okay, so taking a step back, we ask ourselves what protocols and computations are autonomously offloadable and to define the properties that make them such. And we find that most computations and protocols are offloadable, but not all. So looking at the properties that make computations autonomously offloadable, we start by identifying that on the transmit side, the computation must be size preserving. And this precludes acceleration of compression and encapsulation. And for instance, we have here an example with encapsulation to explain the intuition behind this. So suppose we have two hosts, host A and host B, communicating via TCP, and host A uses a NIC that inflates the message, say adds TLS headers or something of that sort. I think I lost control again.
It's just a little slow.
Oh, okay. Okay, so host A sends the first packet and the NIC accelerates it by encapsulating it. And by doing so, it adds some additional payload bytes. And as a result, an additional packet is required because the MTU is exceeded. So 2 packets are sent on the wire instead of 1. So host B receives those 2 and sends X. But the second ACK is lost. And as a result, what we get is that host A thinks that all the data it sent has been successfully received because it got an ACK for the 150 bytes it sent. But in fact, some data was lost and the NIC needs to be responsible for this retransmission. But retransmissions and TCP logic is what we wanted to avoid placing in the NIC. And this is why we consider this undesirable and a property that is required. Next, we require that the computation is computable on TCP packets of any size. So it can't require any bytes from future packets. And this precludes some block ciphers such as AES-CBC, which operates on blocks of 16 bytes because some packets may not contain all of those 16 bytes and we need to pass them on. We don't want to start storing packets in hardware to perform this operation. Next, to do the recovery, we require that the state required to compute the operation is of constant size and is message independent up to maybe some metadata such as message sequence numbers. And it cannot depend on all stream payload or on future bytes. And we find that most protocols adhere to this. So indeed, many computations fit these requirements, and this includes as a copy, to offload with zero copy, and HTTPS, which is just using OpenSSL. And what we can see in the figure, for instance, starting from the left figure with the throughput, is that the yellow line and the blue line, they're more or less the same. And the yellow line is an optimum. HTTP is the best we can hope for when doing HTTPS with offloading. And we see that the gap is very small. And the numbers below show the comparison between HTTPS and offload with zero copy. So on the leftmost point, we improve performance by almost twice. And on the rightmost point, with 128,000 connections, it's improved by 53%. Okay. So finally, this result is somewhat similar to results that Netflix show using FreeBSD with the same hardware. They're working now on doing this on 800 gigabits, and this is all public. You can look it up. That's it. In conclusion, autonomous NIC offloads is a framework for accelerating layer 5 protocol computations efficiently while cooperating with the software TCP IP stack. It is applicable to most protocols and computations, and the evaluations show that we can improve throughput by 3.3x and reduce CPU utilization by up to 60% and latency by up to 30%. Thank you.
Okay, thank you. So are there any questions for Boris? Surely someone must have a question. All right, so I have a question. So obviously this approach assumes certain properties of the protocols. It assumes they're size preserving, incrementally computable, have constant state, and so on. And obviously these fit some protocols, but not necessarily all of the protocols. To what extent are these sort of fundamental limitations of the approach versus sort of limitations of the current work that might potentially be resolved in a future iteration of the ideas and the approach?
So almost all of them are fundamental. The only one that can be somewhat softened is the requirement for CBC. Well, it's possible to think of a solution that stores some bytes to enable this offloading the partial block, the one that doesn't have the full AES block. But this would be more complicated, and ASCBC is deprecated, so there is not much interest.
Okay, thank you. Dave.
Hi, Dave Oran, MIT. Do the trade-offs change at all if you have a user mode TCP stack as you would with DBTK or something like that?
Not at all.
Okay, thank you.
Any other questions? Anyone on the remote maybe have a question? Okay, so one other thing, I mean, obviously this is an IETF meeting that you're presenting at. Is there any sort of guidance or any sort of issues to consider that the IETF should be paying attention to when designing future protocols to make this type of approach or similar approaches sort of work better?
Yes, actually, that's a great question. So this approach also works for TLS 1.3, which was finalized more or less when we were finalizing the hardware. And one of the things that happened in TLS 1.3 is that the trailer was starting to use the real application type, and when using an offload such as this, it created some problems. For instance, So in general, it worked well because the format of the record remained the same. So keeping the formatting of records the same is helpful. But one problem that appeared is that until we decrypt the entire record, we don't know if it's an application, really an application data or something else. And this becomes a problem when we want to combine this with something else. So suppose inside TLS we have some protocol that we parse and we use to do data placement. So to do data placement, we need to assume it's application data, but if it's a handshake, then it's bogus. And this creates quite a lot of complexity that we didn't anticipate, that doesn't exist with TLS 1.2. So this is somewhat unfortunate. Similarly, the padding is also makes things more complicated than it could have been.
Okay, thank you. So it sounds like there's maybe some lessons that can be learned from the way the protocol design changed to simplify offloading.
I'm not sure that the IETF wants to standardize according to the way hardware works, but it would have been desirable, of course.
Yeah. But it perhaps helps if there are multiple ways of designing a protocol, and some are easier to offload than others.
Yeah, definitely.
All right, I see Rod Van Meter.
Yeah, Rod Van Meter, Cary University. This looks like really good work. Thank you. It's an interesting presentation and I think important topic. This might be kind of an extension of Colin's question, but to what extent is this work, the value of this work, sort of a characteristic of this particular point in time relative to the technology? Is this a future-proof technique? Will we still be able to use what you've been doing 10 years from now, 20 years from now, as the technology continues to evolve? For example, if somebody, sort of a corollary question is, if somebody offers you one parameter to change to the system that might get better, how would that affect your performance? If somebody offers you doubled bandwidth or twice as many cores or something.
That's a great question. So these are the early days of this technology in particular, so it's hard to predict what's going to happen in the future. Right now, we're seeing some adoption, but it's not like everybody needs to do 800 gigabit TLS. So it's not obvious that it's applicable to all use cases.
Yeah, they're impressive numbers.
Yeah, the numbers are great, but not everybody needs those numbers. So there is a trade-off there, and making the most out of it requires quite a lot of work in software. I think the performance in FreeBSD today is somewhat better than Linux, because the Netflix guys really did a lot of work to make it so. I think we'll see over time how it evolves. The trend is that CPUs are not getting much faster, while NICs are getting very fast, and it makes sense to move as much data-intensive computation over the payload to the NIC as possible. And as long as we are using TCP, I think this technology is going to remain relevant.
Thanks.
All right, thank you. Are there any final questions? No? Well, in this case, congratulations once again. Thank you. All right, congratulations once again. Thank you, Boris. Next up is Arthur. So pass you control and then do a quick intro. Okay, so the final talk today is the other Applied Networking Research Prize winning talk. It is by Arthur Seller Jacobs. Arthur has a PhD in computer science from the Federal University of Rio Grande do Sul in Brazil. And he's worked with Jennifer Rexford's group in Princeton and with Walter Willinger. His research interests include network management, intent-based networking, natural language processing for network management, self-driving networks, programmable networks, and artificial intelligence, and its applications for networks and security. He's working currently as a senior software engineer for Nomad Health, I believe. And his paper today is entitled AI and Machine Learning for Network Security. The Emperor Has No Clothes. And I believe this was originally presented at the ACM Computer and Communication Security Conference in November 2022. Yes. Okay, you should have control over the slides. So I do. Go ahead. Thank you.
Thanks, Colin. Can I pull this up? Maybe.
Maybe.
That's better. Is it? Yep. Okay.
Talk right into the mic.
Oh,
Very
right into the mic. Okay. Thanks, Colin, for the introduction. Hi, everybody. My name is Arthur, and I'm here today to present to you our work entitled AI/ML for Network Security. The Emperor Has No Clothes. So in recent years, we've seen exciting advances in machine learning and AI in fields such as facial recognition, recommendation systems, or even spam detection, among many other areas of computer science and other areas. But let's take a look at what's causing all that excitement and what we call the traditional AI/ML development pipeline. Usually, if you want to develop a new machine learning model, you start by collecting some data and selecting which model you want to use. You then use that data to train your selected model and evaluate it using traditional evaluation metrics such as precision, recall, or F1 score. Then, if you have a high enough F1 score, that usually means your job is done. You can claim your model works, deploy it in a network production, and you move on. Otherwise, you go back, you collect more data, or you collect better data, and reevaluate your model selection. Now, we claim that this sort of traditional AI/ML pipeline is good enough for low-stakes decision-making, such as recommendation systems or spam detection. But what about high-stakes decision-making scenarios, such as self-driving cars or network security, in which a wrong decision can have direct impact on people's lives or companies' revenues and reputations? In these scenarios, we argue that we need to be able to claiming that a model works is not good enough. We need to be able to tell why a model works and when does the model not work. Consider, especially consider that it is well documented that machine learning models can suffer from underspecification issues such as shortcut learning, where the model takes shortcuts to classify the data rather than actually learning to solve the problem, or that a model might suffer from out of distribution samples, or even that the model is simply overfitted to spurious correlation in the data and not learning anything. Consider this example. We trained a random forest classifier on the popular dataset SeqIDS 2017 for network security and achieved a F1 score of 0.99. In this example, if we revisit the questions we asked before, we quickly realize that the traditional AI/ML pipeline gives us no answer to them. So in this specific scenario, would you be able to trust this model? When trusting this model actually means handing over control for that model to make its decisions. So to help developers and researchers answer that question, we propose Trustee. Trustee is a novel explainable AI technique that produces global explanations from any machine learning black box model in the form of high fidelity and low complexity decision trees. Trustee augments the traditional AI/ML pipeline with two new steps. The first one to extract a decision tree from any black box model, and the second one to analyze that decision tree for any issues that might be impairing the model to make the correct classifications. Let's focus first on this step, the explanation. When designing Trustee, we had four major requirements in mind. The first one, for it to be model agnostic, for it to be able to work and explain any given machine learning model and not a specific type of machine learning model. The second one was for Trustee to be able to produce high fidelity explanations, that is, decision trees that makes the same decision as the black box model. The third one, and since this decision tree is meant for a human to be able to parse and understand, we needed the decision trees to be low complexity enough so that a human can actually parse it. And finally, our last requirement was for trustee to be able to produce stable explanations. That is, produce roughly the same explanation for the same input on multiple executions. So trustee's algorithm starts receiving as input to a data set and a black box machine learning model. It then starts by splitting that data set into a training and testing data sets using a given split, such as 70 and 30%. It then uses that black box model as an oracle to produce the expected output for the training data, which will then be used to guide the training of the decision trees. Notice that since any machine learning model can be used to produce the expected output, we achieve already our first design requirement of model agnosticity. Then, trustee selects an M number of samples from this training data set and expected output, and further splits it into a training and testing set. The training set is then used to produce a decision tree using the traditional algorithm CART, classification and regression trees, and then evaluated using the testing data sets to produce an explanation output, which we can then use to measure the fidelity of the produced explanation with the expected output. This process is repeated another time and an M number of times with different samples from the training data set, in which we call trustee inner loop that runs an N number of times. This inner loop produces an output, the decision tree with the highest fidelity achieved on all iterations, achieving our second design requirement of high fidelity. Then, one thing to notice here is that it is not uncommon for CART's algorithm to produce decision trees of hundreds or thousands of nodes. And for a human to be able to parse it, this needs to be much, much smaller. So the size of the explanation here matters. To circumvent this problem, we propose a new pruning algorithm we call top K pruning. Top K pruning is based on the observation that if you rank the branches of a decision tree based on the number of samples that it covers, you get diminishing returns in terms of fidelity. So we pruned the outcome explanation by simply selecting the top K most important branches from a decision tree, which will give you the most fidelity for it. Achieving our third requirement of low complexity. Now, finally, given that a trustee uses a subsample of data to train decision trees, it is possible that with multiple executions, different decision trees will be generated. And so to mitigate that issue, we added an outer loop to trustee that runs the inner loop for an S number of times and calculates the pairwise agreement of the decision trees produced. That is, trustee measures whether or not the produced decision trees agree on the decisions made for the same samples, and then returns the decision tree with the highest mean agreement amongst all of them, achieving our last design requirement of stability. This decision tree is also the final output of trustee's algorithm, which is then presented for an operator or developer that's using trustee. Now, for the second step of the augmented development pipeline, we introduce a novel method we call trust reports. Trust reports basically automate part of the analysis process to try to identify the underspecification issues that I'd mentioned before, that shortcut learning, out-of-distribution samples, and spurious correlations. The trust report summarizes important information from the decision tree explanations, such as the size of the decision tree, the depth, the number of input features from the model that were actually used to classify the data, the fidelity, amongst many other things, and small experiments to see how much the explanation is faithful to the actual black box. On top of that, the trust report produces useful plots on the decision tree explanations, such as the number of samples classified at each level of the decision tree for optimal pruning, the number of samples and classes that a specific branch classifies, and then the number of samples that each feature is responsible for in the decision tree classification. Now, it is important to notice, though, that the trust report does not automatically tell you which under-specification issue your model suffers from. It still requires a human to look at them and try to identify it, since these under-specification issues are ultimately domain-dependent. So it's really hard to automate. We did try. Now, to illustrate how trustee can be used to scrutinize machine learning models, I brought you 3 use cases I'd like to discuss. The first one, all of these use cases, by the way, are from selected publications with reproducibility artifacts available online. So the first one is a one-dimensional convolutional neural network used to classify data between VPN encrypted traffic and non-VPN traffic. This model uses the first 784 raw bytes from each PCAP file analyzed, and reported an F1 score of 0.99. We were able to reproduce something close to that of 0.96. We then used this model to extract a decision tree out of it using trustee with a fidelity of 1 precisely, and no pruning was required since it only had 7 nodes that you can see here on the screen. Now, as you can see, this decision tree is telling us that the model is using bytes 49, 43, and 47 from the input bytes to make the classification between VPN traffic and non-VPN traffic. Now, to understand this decision tree, we need to first understand the data that it's coming from. So if you go, when we went and dove deep into the PCAPs that were being used, we quickly noticed that there was a split in the data. That is, all the non-VPN traffic PCAPs had Ethernet headers on them, while the VPN traffic PCAPs did not have Ethernet header on them. This created a mismatch. This created a mismatch of the alignment of the features that the model was looking, because for non-VPN traffic, the model was looking at source and destination MAC address headers, while for VPN traffic, it was looking at total length, flag offset, and protocol from the IPv4 headers. So with that knowledge in mind, we can go back to the decision tree and see that the first decision that this model is looking at is basically comparing whether or not for VPN traffic, it is using the UDP or TCP protocols, value 6 and 17 of the IPv4 protocol, against a random byte from a source MAC address, which in this case is always larger than 17 for the data. So that basically splits almost all of the data perfectly. The second level of the decision tree is basically showing that to weed out the remaining few samples that do not follow these rules, like 1%, the model is picking up on different headers, such as the fragment offset against a random byte from the source MAC address for VPNs on the right side, and on the left side is looking at the destination MAC address, which is always 0. So with that in mind, we set out to produce a validation data set to validate the explanation output. And we did that by tampering with the packet headers from the original PCAPs, specifically headers 43, 47, and 49. And as you can see, that had no impact at all on the model's precision and recall. The reason for that, and using our trust report, we were able to identify that, is that if you go back to the data, you quickly realize that the developers of the model didn't remove the PCAP metadata from the PCAPs before reading the features. So they're actually reading feature values from the PCAP metadata for the first 40 bytes, which includes a lot of potential shortcuts for the model, including byte 3023, which indicates whether or not the Ethernet header is present or not in the PCAP. So from the first few bytes, the model had plenty of opportunities to take shortcuts to classify the data rather than actually learn to classify between VPN and non-VPN traffic. So with that in mind, we set out to tamper with ranges of feature values rather than individual features, from 32 to 63 to 0 to 63 and to 0 to 127, until we reach an F1 score of 0.398, which is basically worse than a coin flip. So The takeaway is that this model is suffering from blatant shortcut learning and didn't learn to classify the data at all. And it's simply picking up on shortcuts put in the feature values. Now, for the second use case, I want to revisit the random forest example that I showed before. We selected many papers. We saw many papers that relied on the SeqIDS 2017 dataset for classification. This dataset is really popular. This dataset contains traffic from 13 different types of attacks, aside from benign traffic, including port scans, DDoS, and Heartbleed. And this dataset comes with a set of 78 pre-computed features from flow statistics, such as flow duration, mean inter-arrival time, number of packets sent and received in each flow. And a lot of, most of the publications we found that used the dataset reported F1 score numbers of 0.99, which were very easily able to reproduce with a random forest classifier. We then used trustee to extract a decision tree from this model, which gives us a 0.99 fidelity, of which you're seeing here the top 3 pruning of it, which only has 6 nodes. Now, aside from the obvious problem of using destination ports to classify FTP and SSH Patator attacks, I want to focus here on this specific branch that classifies all of the Heartbleed samples in this data set by simply looking at the maximum length of the response packet size in the flow. By simply looking whether or not the maximum length of response packet size is bigger or smaller than 12K, this model is able to determine whether it's a Heartbleed attack or not. The reason for that, and using this distribution plots from the trust report, we can see that this feature specifically perfectly splits the entire Heartbleed flows from all of the rest, because the response packet size for Heartbleed flows is always bigger than 12K, and it's always smaller than 12K for all of the other classes. And we can see that same behavior in other features, such as the inter-arrival time, response inter-arrival time, which almost perfectly splits Heartbleed from all of the other classes. Now, to understand why this happens, we need to first understand how the Heartbleed attack works. A Heartbleed attack, and I feel like this is preaching to the choir, but the Heartbleed attack happens when a malicious actor sends an HTTPS heartbeat message to a vulnerable server with a value in the size field bigger than the actual package. So basically, you can send a 16K byte packet and specify it as 64K bytes for the server. A vulnerable server will respond with a message with a heartbeat response with the same size as the incoming packet by copying the context of the incoming packet into the response packet. So, but since the incoming packet only has 16K bytes, the response packet will have 48K bytes from the server memory, which may include credit card information, usernames, passwords, that sort of thing. Now, in the SeqIDS 2017 dataset specifically, we notice that for the 30 minutes duration of the Heartbleed attacks generated, they didn't close the connections once. We generated huge numbers for feature values related to response packet sizes and inter-arrival times in those flows, which made it abundantly easy for the model to pick up on those values. So with that in mind, we set out to generate a validation data set for our explanation, consisting of 1,000 new Heartbleed flows with out-of-distribution values, in which we simply close the connection of the HTTPS connection after every heartbeat message sent. And this generated feature values related to response packet sizes and inter-arrival time, much similar to benign traffic. And as expected, the random forest classifier was unable to identify a single one of those new 1,000 Heartbleed flows as Heartbleed. So the takeaway for this specific use case is that this model is clearly overfitted to training data and suffers and fails to identify any simple changes or simple out-of-distribution samples. Now, the third use case, and last I don't want to show, is another example of a paper that uses the SeqIDS 2017 dataset. This paper was published in CCS 2020 and proposes a model called nprintml. This paper uses an AutoML model for intrusion detection system and uses 4,480 features with values -1, 0, or 1, which correspond to a stable bit representation from the packet pre-established protocol headers read from the 5 first packets of each flow. Basically, if a header is present is not present in the packets, the value is set to -1, and it's set to 0 or 1, depending on the value that is set in the packets. This model achieved an F1 score of 0.99, which we were easily able to reproduce with their reproducibility artifacts. And then we used TrustE to extract a decision tree explanation out of it with a fidelity of 0.99 again. And as you can see here, the stop 4 pruning of it only has 8 nodes from that tree. Now, there's a couple of different interesting things to focus here. The first one of which is that the first decision of this decision tree is making is basically looking at the TTL of the first packet and checking whether the third bit from the TTL is 1 or 0. The reason for that is that because in this data set, all of the attack traffic was generated from an outside computer 1 hop away from the measurement point. And so this is basically checking whether the attack was inside the network, benign, or outside the network, which is malicious. So it's basically able to tell the difference based on that. Most of the attack traffic was generated using Kali Linux, which is initial TTL value is 64, -1 hop, 63, third bit, 1, and then you get to split all the benign traffic from the rest. Now, the second decision is also looking at TTL, but it's splitting all of the DDoS attacks that were generated using Windows 8.1 to be specific, which has an initial TTL value of 128, -1 hop, 127. So it's looking at the second bit of the second packet. It could be the first packet. So yeah, whether it's 1 or 0, and then it's able to identify all of the DDoS samples in this data set. Now, the third decision that here is also interesting because if you notice, the decision tree is checking whether or not the value is negative or not. That means that the model is checking whether, no problem. This means that the model is checking whether there is a second packet or not in the flow observed. As most of you probably know, port scans are usually not responded to by an attack, by a victim. So all of the port scan flows in this data set only had 1 packet. So basically the model was able to check whether or not it was a port scan by checking the number of packets in the flow. And finally, this was our last observation. We noticed that this decision tree relied heavily on random bits from the TCP options headers in the flows, and using the truth report, we iteratively removed features from this data set until there was only TCP options fields for this model to pick up on. And still, this model reported an F1 score of 0.99 using only TCP options bits. So this was very interesting to us and indicated that this model was not learning anything, but was picking up on spurious correlations in the data. We set out to validate this explanation by curating a balanced data set of 4,047 flows from real-world traffic from UCSP network, and use Suricata IDS to label those flows between benign, distribution of service attacks, and port scans, which were the 3 classes that we were able to collect from the short span that we collected. As you can see, when we used nprintML model to classify that data, it was unable to identify a single one of the distribution of service attacks, denial of service attacks, sorry. And it was able to identify very few of the port scan attacks. The reason for that is because, as I mentioned before, UCSP also didn't respond to port scan attacks. So it was able to pick up on a few of those attacks based on the number of packets in that flow. But as you can see, it failed when put under minimal stress of real-world traffic. So our takeaway for this is that this model suffered from spurious correlations in the training data. And the reason for that is that it's because of an issue called curse of dimensionality. This feature, this model has a so large number of features that is not able, the training data is not able to cover all of the possible feature values in that data, making it abundantly easy for the model to pick up on spurious correlations in the data like this. So aside from these three use cases that I presented, we looked at 4 other different use cases with reproducibility artifacts available and found similar issues in all of them, including Kitsune's ensemble of neural networks for anomaly detection, and Pensiv's reinforcement learning model for adaptive bitrate selection. In the paper, you also find an algorithm description of trustee, an ablation study on all of the design requirements that I presented, and more information, as well as a user guide on the trust report that I mentioned before. Trustee was also packaged into a Python package that can be downloaded today. It's available for anyone to use, and has received surprisingly amount of downloads already. And finally, machine learning in high-stakes scenarios requires a level of trust that the traditional AI/ML pipeline simply cannot give us, but Trustee helps by improving the trust and providing high fidelity and low complexity explanations in the form of decision trees. Trustee can be used today by anyone and be downloaded in that website or using pip. And yeah, so just download the Python package and go analyze. So yeah, thank you.
Thank you. All right, thank you very much. Excellent talk. Does anyone have any questions for Arthur?
Hi, Stephen Farrell. Yeah, I read the paper. It's a really good paper. Thanks. I enjoyed it. I have to say, I enjoyed reading the paper when I got towards the end. The beginning was a little bit harder work for me because it's not my field, but the end actually was very good when you used it with the case studies. So I was wondering, all of this depends on having access to the training data, essentially, right? If you don't, and perhaps in a lot of real world cases you won't, let's say if a vendor is making some claims or something, is there any way to kind of envisage that you could extend this to handle cases where you don't have access to the training data?
Yeah, so you technically don't need the exact training data to produce an explanation using Trustee. You just get better insights using the training data. But if you have access to the model, say through an API that makes the classification, and you have data that you are able to use to test it, you can produce explanations for that data for using that model. But that is a hard challenge because not everyone makes the model available like that through an API, for example.
And so as a follow-on, then, could you envisage that there could be any recommendations you could make to people who are claiming that their models are super good, things that they could make available that would allow some kind of validation like this? So maybe make an API available, or, you know.
Yeah, so this is part of what I mentioned before about we try to automate this analysis as much as possible, but it's really hard because it's hard to tell whether or not the model is actually suffering from shortcut learning, for example, or the problem might be super easy and not need machine learning at all. So it's hard to make that call unless you're actually familiar with the domain. But we did have like a bunch of guidelines based on the values we produce on the trust report that could indicate whether or not there might be something going on with the model. So for instance, if your model has 4,000 features and you're using 1 or 2% of it to make a perfect classification using a decision tree, that is probably an indication that there's some problem going on. We can't say for sure, but that's an indication we can tell. A recommendation for people to check.
That's great. Thanks again. And it's nice to see somebody being skeptical. But
thanks.
Hi, Doug Montgomery. Is there some notion that your resulting decision tree model is unique or optimal in some way, or are there?
That is a good question. So it's not. I would say it's not unique, and probably not optimal. We optimize for fidelity, but there are different decision trees that might result in the same fidelity. When we achieve the best possible fidelity for the use cases we analyzed, but if you have correlated features in the data set, you could generate a decision tree of the same fidelity with using different features, for instance. So we chose not to tap that information basically by adding that outer loop to trustee to produce a decision tree that's roughly stable. But one of the things that we discussed while developing is that there is knowledge in the different decision trees that you may produce. The expressivity of a decision tree is naturally lower than the neural network, for instance. A neural network has more power, expressivity power, than a decision tree. So, and that's the reason we moved away from decision trees in the first place. So you can produce different decision trees explanation for the same neural network, and they all might be true. It's hard to say. It's hard to say which one is the one true decision tree. Probably there isn't one. It's an amalgamation of all of them, and that's something we're kind of working on, trying to tap on the information of different decision trees that might be produced, because they can be there can be valuable information there to explain how the neural network might be working, for instance. Does that answer your question?
Yes.
Yeah, okay.
I had a quick second question, just to be sure, right? When you produce these curated data sets, you are retraining on them, right?
No. We are evaluating the model as trained originally on the curated data sets to see how they would perform.
Okay.
Okay, I see Brian Trammell, I think, is remote.
Well, let me pop myself back out of the queue. Oh, no, wait, I was supposed to keep myself in so people know who I am. Hi, I'm Brian Trammell. Good morning from Zurich. So I noticed something in, thanks a lot for the talk. This was great. Unlike Stephen, I haven't read the paper yet, but I'm going to fix that this week. I noticed something in all of your examples where basically you went into the decision tree and were essentially doing analyses based on fairly deep domain knowledge of how the senders in a network operate, right? And this is something I think that's been missing from at least a lot of the ML literature on apply ML to network security in the past. So thanks a lot for that. Is it accurate to characterize the work that you've done here as basically automation assisted analysis of these decision trees, right? Like, so the what trustee gets you is over the first hump to point out, hey, you should look here for an overfitting or an overclassification. Is that an accurate? Have I understood that correctly?
Yeah, mostly.
Okay, cool. So one of the things that popped into my head when Stephen was talking, and this might be something to look at in sort of future work for looking at being able to do verification without training data, is you can essentially generate synthetic network data based on your knowledge of how these stacks work, right? Like, so the set that you have to explore if you're trying to extract something from an API is significantly reduced from the set that you, and even just in the examples that you have here, you have a lot of examples where it's like, oh, I can tell I have PCAP metadata versus not, or I have the Ethernet header versus not. I mean, there's a highly restricted set. So I think this is more of a, for follow-up work, I'd really like to see sort of like an extractor come out of that. So that would actually get you to the next step of being able to automate this analysis. Because it did look a lot like, it looked a lot like, okay, we used the automated thing and then a human had to go look at it, which is super useful, but has some scalability issues.
Yeah, understandably. Yeah, that's actually a very good idea. As a reference, I can point to at least there's a Hotnets paper that came out in 2021 that did something similar using ALE plots, but they didn't generate the data. They used ALE plots to sort of guide the collection of more data to cover more data points.
Okay, cool.
So it's something similar to what you mentioned. Yeah, but I could see something like that being automated.
Thanks a lot, and thanks for the talk. This is great.
Thank you.
Okay, thank
Hi.
you.
The start of the paper, thank you for this talk. It was really nice. The start of the paper is about how you're explaining the models, right? But as I go further on, it's more like you're also commenting on the data set. So that just because I'm familiar with the data excellence work, when you must have heard the data sheet for data sets.
Mhm.
I just think that this has a lot of applicability in knowing how to do not just model explanation, but characterizing the data set itself.
Yeah.
I mean, that I think is very new. And another thing is the fidelity score that you have is you've shown that with the precision recall and F1 score. Have you considered doing a specific information gain measure?
I know I have not, but that's a good point I can look into.
Thank you.
Regarding the data,
Yeah.
we did notice that most of the problems we identify with this model arose from the bad data or from using the data wrong, basically. So we had this debate a lot while developing whether we were finding issues with the model or with the data, but in the VPN, non-VPN example, for me, choosing which features to use, that's part of developing the model. So that's also an issue with the model, even though it's coming from bad data. So they're very intricately connected, and some of the reviewers pointed it out to us. So it could be used to guide how to get better data or excellence in data, as you mentioned.
Yeah, because like I'm coming from an NLP domain, and there are these very good, well-known data set benchmark data sets, which have been like really exceeded by current algorithms. But then those data sets are, as you have shown with the network data sets, are also in a sense biased.
Mm-hmm.
So I just think this work is.
All right, thank you.
All right, thank you. That was Priyanka. Diego.
Is this no? Okay, so well, the one bending Diego Lopez. No, it's related precisely with these comments on the data set, etc. When we started to work with AI models, I insisted very much that if we were network management practitioners, etc., we should focus more on the data than on the models. And we have been trying to set up mechanisms for publishing data sets that are usable for making, and when you make this reflection about getting the model plus the data, because otherwise trustee cannot make, or it's much more difficult that you can make any sense. I was wondering whether, well, not necessarily in the IETF or the IRTF or whatever, whether it would be advisable that we try to push for a set of public data that could be equivalent to open, I don't know how to call it, open source AI or open data AI or whatever. It's just, I felt myself vindicated, and I wanted just to comment it and to ask you if you share that view.
Yeah, thank you so much. That is part of, we do comment on that in the paper, that sharing data in networking is different from other areas that took advantage of that in AI, such as images or text, because there's a lot of private data in networking, and people are not willing to share that. And at this point, I think there's been some initiatives like the people that produced Seek IDS 2017 to produce data for machine learning that's publicly available, but they're all fundamentally broken, that they make them kind of useless for us. So at least the alternative we found was for people to work with their universities. We couldn't publish, for instance, the UCSB dataset because that was private for the data. We did publish the headers only, not the payloads of the traffic. But it allowed us to at least validate the model that was trained on a different dataset. So that was the alternative we found, and I think might be the one that we as researchers can take advantage of.
One of the things that we are trying is to convince the European Commission, at least, to fund this kind of data sets. We're becoming to be successful. So it's something that it will take time, I'm afraid. Yeah.
Great.
All right, Doug, one last question.
So I'll ask what I wanted to ask after the previous question. So did you reevaluate the models using the synthetic data or the curated data as the new training set?
I'm not sure I follow your question. Did I?
So I was asking when you had these, more interesting data sets or curated or synthetic, whatever you want to phrase them, you're using the originally trained model and now a new data set to evaluate them.
Yes.
Did you turn around and retrain the models on the synthetic data sets? I'm trying to figure out if you're saying something about the robustness of the model or just that it was poorly evaluated and trained in the initial paper.
That's a good question.
Because what you present, has shocking or interesting results from 0.99 to 0 is interesting, but it's not quite giving it the chance to retrain on the better data set if we're talking about the robustness of the proposed technique.
Yes, but I would say the idea of this proposed is not to retrain, right? You're publishing a black box and this is your solution to it. So their idea is basically to take this box and put it in a production network and it should work. That's sort of how these models are sold to us, and not that you need to constantly be retraining it as you should. So our idea with validating those papers and that on the data that was used was simply that curating a different data set to show that if you put this in your network as it is, it will break, basically. But we did retrain, if I'm not mistaken, the nprintML model, we did retrain using the UCSB dataset. And he was able to pick up he was able to do better adding the retrained data. But we only curated 4,000 flows compared to millions and millions of flows of the SeqIDS 2017 dataset. So it didn't have a big enough impact on accuracy. So yeah.
Okay.
Thank you. All right, thank you very much. Thank you. Congratulations again.
Thank you so much.
All right, that's everything we have for today. Thank you again to Boris and to Afa for giving the talks. Congratulations on the awards. Both of the prize winners will be here for the rest of the week. So if you have further questions or want to talk about the work, please do go talk to them. Please also consider going along to the usable formal methods group or the RASPRG later in the week and seeing what's going on in those two new research groups. And with that, thank you everybody, and I'll see you around.